Hello, in this session we will solve a sample exam, exam number 3, and the objective of exam number 3 will be to test your knowledge in filter design. You have 4 questions and you are supposed to solve them within 75 minutes. The first question will be around about your general knowledge about filters. So in the first part you are asked to complete the following table such that you have the order of the filter and the quality factor, of the filter. So here we have the passive filter. This has a quality factor or a selectivity of 0.5. The one with 0.71, which is 1 over radical 2, approximately, this is called the Butterworth filter. And for the filter that is greater than 1 over radical 2 is called the Chebyshev filter. In the second question, we are asked to label which one of the plots is for the Chebyshev and the one for the Butterworth. The blue one, is called the Butterworth filter. Why? Because it has a Q of 1 over radical 2, 1 over radical 2, which in the logarithmic graphs gives a flat plot and not steep, flat and not steep, and the quality factor is 1 over radical 2, approximately 0.707. The red one is called the Chebyshev filter because it's steeper and it has some ripples on it with some ripples, and Q is greater than 1 over radical 2. Third question is asking about the order of the filter. We know that as we increase the order of the filter becomes more ideal. So for sure this would be the first, would be the second, third and fourth. And as we increase the order more, fifth, sixth, and then it becomes much more ideal. In the fourth question, you are given a photoplethysmography device used to measure the heart rate. However, this device is subjected to various types of noise, mainly a DC voltage signal, which is superimposed on top of the actual signal. So you are asked to design a filter to remove the DC component. Because the DC component has a frequency tends to 0. So assume, for instance, you have a sinusoid signal. Cosine 2 pi ft or sine. In case it is cosine and the frequency is equal to 0, this tends to be a DC, an offset signal. With a frequency equal to 0, a DC component. So we need to remove the low frequency components. Once we say we need to remove the DC component, this indicates that we need to remove the low frequency. And therefore we need to implement a high pass filter, in order to remove the low frequencies, to attenuate the low frequencies and allow the passing of high frequencies. So we get the input signal, we feed it to a capacitor and resistor, and here we get the V output. asked as well to derive the transfer function and to show its magnitude plot. Okay, we have we label the nodes, okay, using the node method. Okay, this is the ground, this is V0, so V0 minus Vn over 1 over JWC. Okay, the capacitance, the impedance of the capacitance is 1 over JWC, and the impedance of the resistor is R. So this is 1 over JWC plus V0 minus ground over R equal to 0. So we have V0 J omega C plus 1 over R. We bring Vn to the other side, J omega C. Okay, so V0, the transfer function is given by V0 over Vn, which is equal to J omega C. Okay, we may write instead of J omega S the Laplace. Okay, R, okay, we can multiply it, R, okay, R J omega C plus 1. So this is the transfer function. And we need to plot the magnitude to verify that this is a high pass filter. Okay, high pass filter. Okay. Either we use the diagram directly or the transfer function. So in case we want to use the schematic, as omega tends to 0, okay, the impedance of the capacitor will be infinity, and therefore this would be an open circuit. Therefore V output would be connected to the ground, so V output would be equal to 0. Okay, so V out over Vn is, as omega tends to 0, V out over Vn tends to 0 as well, as the impedance of the capacitance will become infinity, and therefore this is an open circuit. This could be modeled as an open circuit. Okay, open. So the V out would be equal to the ground. As omega, the angular frequency tends to infinity, okay, 1 over infinity is equal to 0. This can be modeled as a wire, okay, and therefore V out is connected to the V input. So therefore the V output is equal to V input, okay, and therefore V out over Vn is equal to 1. Okay, so here we have 1. As W tends to infinity, this would be equal to 1, and we can have the following magnitude plot. Okay, of course we need to determine the cutoff frequency on practice. Okay, this is the cutoff frequency at which it exists at 1 over radical 2, 0.7. If we need to modify this into a body plot, remember that this would become a logarithmic graph, and the 1 over radical 2 is approximately 3 decimals. Okay, 3 decimals. Okay, so in order to use this device in practice, we noticed that an athlete would have a minimum heart rate of order 40 beats per minute. 40 beats per minute is the number of oscillations, okay, number of cycles per minute, okay, and therefore this is the frequency, okay. And now our job is to determine the actual values of those components, the capacitance and the resistance, okay. So we are given the cutoff frequency, right? So the frequency, okay, the cutoff frequency is must be less than a minimum of 40. Okay, the minimum frequency of the heart is 40, so we need to remove anything below 40 or the DC in order to remove the DC component. Okay, so we should keep the 40 and the frequencies above. Okay, so we have a 40 beats per minute. This is equal to 40 beats over 60 seconds. This is equal to 2/3 hertz, okay, or cycles or beats per second. Okay, this is the frequency. Okay, so we need to determine the actual value of the cutoff frequency. If we determine the magnitude of this transfer function, okay, this is equal the magnitude of j omega rc, it is omega rc over the magnitude of this complex function is equal to a square plus b square. Okay, so r omega c square plus 1. Okay, this must be, in order to have the cutoff frequency omega c or 0, okay, this must be equal to 1 over radical 2. Okay, so omega c rc radical 2, okay, equal to radical omega c rc square plus 1. Now square both sides. 2 omega c rc square equal omega c rc square plus 1. Okay, therefore omega c rc, okay, this is a subscript, omega c, okay, is equal to 1. Right, so omega, the cutoff angular frequency is 1 over rc, and therefore 2 pi fc cutoff frequency is 1 over rc. Cutoff frequency is equal to 1 over 2 pi rc. Right, the cutoff frequency of the high pass filter must be less than 2/3 hertz. Okay, now because the DC component tends to 0, so we may choose like the cutoff frequency either to be this is on order of 0.6. I mean, we may choose, for instance, 0.1, 0.2, 0.3. Okay, because there is no any other restriction other than removing the DC component. Okay, so let's assume we need to remove everything below 0.6, 0.1 hertz. So we make sure that we remove the DC component and we cap the 40 beats per second that we are trying to measure or to capture. Okay, so if the cutoff frequency is 0.1 and we have a we have the cutoff frequency. Now this is an equation with two unknowns, so we need to choose one of the components, either R and solve for C. I prefer to choose the capacitance. Okay, choose C to be equal to 1 microfarad due to its availability in our labs. Okay, then the resistance would be equal to 1 over 2 pi RC. F, okay, we get R to the opposite side, and this is FC multiplied by C. Okay, this is equal to 1 over 2 pi. The cutoff frequency is taken to be 0.1, and the capacitance is 1 microfarad. Okay, in farad it's 10 power minus 6. Okay, this is equal to 1.6 mega ohm. Alright, So the filter, our filter will become like that. I mean, the high pass filter. So we choose this of capacitance 1 microfarad, sorry, and the resistance of 1.6 mega ohm. This is the input signal, okay, and this is the output signal. Now we have the second question. Okay, on the second question we are asked to design different types of filters, and on the first part we are asked to draw a low pass filter, okay, and with the justification. Okay, so a low pass filter, it is I mean, if the high pass filter we are given the capacitor and the resistor, we need to switch the order. Okay, we could achieve the low pass filter. Okay, so we have the V input, okay, resistor R1 and capacitance C1 connected to the ground, and this is V out. Okay, so this is over J omega C1, and the impedance of the resistance is R1. So as omega tends, the angular frequency tends to 0, 1 over 0 is infinity. This would be an open circuit, and therefore V0 is equal to Vn. Okay, so V0 equal to Vn, and therefore V0 over Vn, V out, V0 equal Vn, therefore V0 over Vn is equal to 1. Of course, we are talking about the magnitude. We are not considering the phase shift, okay? The phase angle, okay? So this is the magnitude, V0 over V input. This is the frequency, okay? So as omega tends to 0, 1 over 0, infinity, open circuit, therefore V0 is equal to V out, okay? Omega tends to infinity, 1 over infinity, this is 0, this would be a wire, so V0 is connected to the ground. And this is a low pass filter. Of course, if we need to determine the cutoff frequency, omega c, this would be at 1 over radical 2, 0.7. Now, this is a passive circuit. Okay, this is a passive circuit. We need to convert it into an active filter by providing an isolation at the output. Of course, we can provide an isolation at the output or at the input. For this question, we need the isolation at the output. Okay, so we just take the same circuit. This is the input. Okay, and we isolate it by a buffer. Okay, at the output. Okay, this is non-inverting. Okay, V0. If we are asked to isolate at the input, we connect the buffer at the input. And of course, we can isolate the output and the input at the same time, but we need an additional one resistor. Okay, we have R1 connected to the buffer. Okay, and therefore we have a capacitor and resistor like that. Okay, this would isolate the input, okay, and the output at the same time. Okay, so we are asked here in order only to isolate at the output, and we are given that it is a unity gain. This indicates that we need to use a buffer. Okay, unity gain. So this is would be V out, and therefore this is V out. Right. So we don't change the form of the output voltage. We only preserve the power of the V output. Okay, the energy content of the signal. Now we are asked to derive its transfer function. The transfer function is the output over the input, and in order to do so, we label the nodes. This is the ground. This node is called V output because we know that in an ideal op amp we have the two terminals have equal voltages. Okay, so because of they have very high impedance inside the op-amp, therefore we have equal voltage, and the current that is passing through it is equal to 0. Okay, so we'll be using the power the energy from the power supply of the op-amp. Alright, so in order to derive the transfer function, we have V out, okay, V out minus Vn over R1, V out minus 0. Okay, so V out minus Vn over R1, V out V0 minus 0 over the impedance of the capacitance, and this is equal 1 over JWC. We can write it as well as, okay, C. So S is equal to JW. Alright. So let's use this one, 1 over SC. Okay, so we have 3 wires connected to this node. Here we have the current that is passing through the op-amp is equal to 0, so plus 0. This is equal to 0. Okay, taking V out as common, 1 over R1, 1 over SC, it is SC, and we get Vn to the opposite side over R1. Therefore, we have V out 1 plus, okay, this is the C1, we labeled it, over R1. The transfer function is given by the V output over the V input. Okay. This is the transfer function of our low pass filter. This is the low pass, this is the active filter, okay? Active filter. That's good. Now we are given the general form, okay, of the transfer functions of the filter, the low pass filter, okay, and we are asked to find if it is in the following form. So this is in S domain, such that S is equal to J omega, okay. So this is in S domain. Now we can write the transfer function in this form, such that A1 is equal to omega C R1 C1. We need to find A0 and explain and justify what is S in this transfer function. So what is the difference between this and that? From where we get, if we compare it, okay, we can say like A0 is 1 and A1 must be R1 C1. Why it is given by omega C R1 C1? Okay. Remember that S, as we discussed inside the class, that S is the normalized presentation of the transfer function. Okay. So this S, small s, okay, the small s is the normalized frequency. Okay, normalized frequency with respect to the cutoff frequency is the normalized presentation of the transfer function. So we want to express the frequencies with respect as a ratio with respect to the cutoff frequency. Okay, transfer function. So we can get this transfer function V out over Vn, of course, in the S domain. This is equal to 1 over 1 plus, we can multiply by omega C up and down in the numerator and denominator, omega C over omega C capital S. Okay, so the S, okay, the S over omega C is the normalized. We normalize it, we divide it by omega C. This would be small s. Okay, so it is equal to 1 over 1 plus R1 C1 omega C small s, okay, such that s is the normalized frequency, okay. Therefore this is A1, okay, this is A1 by comparison, and this is A0, okay. If this is equal to AS, so A0 is equal to 1 and A1 is equal to omega C R1 C1. Now we designed our low pass filter. We want to get this filter into practice, okay. Now we are asked to design a low pass filter with a cutoff frequency of 1 kHz. We are given the cutoff frequency, okay, so the cutoff frequency is equal to 1 kHz for the following orders. We are given the first order with a unity gain low pass passive filter, okay, and it is of first order, okay. So in order to use unity gain, it is a unity, okay, as we did so far. Now we need to design the passive filter, okay, of first order. So we can refer to tables, okay, of the passive. This is for Chebyshev. This is for passive filter. Those are the coefficients of the first order passive filter, okay, low pass filter. So A1 is equal to 1 and B1 is equal to 0, okay. So we have A is equal to 1. So A1 is equal to 1. Therefore, if we use this transfer function, this is A1, okay. So A1 equal to 1, which is equal to R1 C1 omega 1, or the cutoff frequency omega C, okay. We are given the cutoff frequency, okay, and we need to solve for R1 and C1, okay. So we make a choose either of R1 and we solve for C1, or we choose C1 and solve for R1, okay. So this is equal to R1 C1 2 pi FC, okay. Assume let choose the capacitance, okay, 47. Always make sure to choose the capacitance and solve for the resistance, because the resistance is easily found in the laboratory than the capacitance. So 47, for example, nanofarad, okay, then the resistance must be equal to 1 over C1 2 pi FC, okay. This would be equal to 1 over 47 times 10 power minus 9 farad 2 pi times 1 times 10 power 3, okay. This is equal to 3.38 kilo ohm, okay. So if we put the capacitance on the above 47 in the above circuit, okay, capacitance 47 nanofarad and the resistance of 3.3 kilo ohms, then this would be a first order filter, and this is called a low pass passive filter. And therefore, if we, okay, with a unity gain, with a unity gain. Now we are asked to find the first stage with a unity gain of the third order low pass filter. We know that in order to design a low pass filter of third order, we need to have a first order, okay, first order, and we need to determine A1. Then we need a second order. We cascade the filters, okay, a filter of first order and a filter of second order. Okay, and we need to determine A1, B1, okay, because of polynomial of second order. Okay, and we get the B out. Now we are asked only to find or design the first portion, the first stage of the third order low pass filter. Remember that we discussed inside the classroom, in order to design first order, we are given this one, okay? Okay, this is the first order, this is the transfer function of the first order. Okay, we only need A1 and B is equal to 0. On the second order, we have a characteristic equation of second order. We need to determine A1 and B1. So of second order, we need A1 and B1. Now, in order to design a third, fourth, or fifth, we make use of the first and the second. We cascade those two filters. A third order would be a first one with a second. A fourth would be a second and a second. Okay. Fifth would be the first, second, second. So if we look over the pattern, if the order of the filter is odd, therefore we need first order cascaded with the second orders. And if the order of the filter is even, like in this case fourth or sixth, we can make use of the second order filter only. Okay. Back to our exam. Okay. In this question, we are only asked for the first order. Okay. I mean, no, for the third order, but we need to solve for the first stage, the first portion of the filter. Okay. This is the input. Okay, so the first order, okay, we refer to the table as well. Okay, Passel filter. This is a Passel filter. This is the third order. Okay, we need to cascade two filters. The first one has those coefficients, and this is the second one. So we have the first one as an A1 equal to 0.756, and the second order, the second filter as A1 or A2 is equal to 0.9996, B2 is equal to 0.4772, and we solve for the capacitors and resistors, the components of the filter. Okay, now we are only asked for the first one. So A1, okay, is given by 0.756. So again, R1, similarly, we can use the same formula. R1 is equal to 1 over A is equal to 0.756 over C1. Okay, let's take C1 against 74. Okay, choose C1 equals to 47 nanofarad. This will be 47 times 10 power minus 9. Okay, multiplied by the cutoff frequency times the cutoff frequency is 10 power 3. Okay, kilohertz. Yes. So this would be equal to 2.56 kilo ohm. Okay. Now let's move forward. Okay, those are the tables. Now we are asked in this part, what is the name of the above topology? We are given this filter. Okay, what is the name of this topology, and which order? Of course, we discussed this inside the classroom, and we said that this topology is called the sallen topology low pass filter. Okay, why it is the low pass filter? Because we have capacitors there and those two resistors. Now if we switch those two resistors with the capacitors, surrounding on two capacitors, okay, and a resistor and resistor instead, this would be a high pass. Okay, this would be a high pass filter. Okay, this is a low pass filter. Okay, so this is a sallen low pass filter, of second order. Okay, second order. Why it is of second order? If we determine the transfer function of this sallen key, then we can obtain the characteristic equation is of polynomial of order 2. Okay, it is of second order. Now we are given we need to modify the above circuit to provide a unity gain. This is very important topology. Unit gain, we need to have a feedback, of 1. Okay, so the V out is returned back as back like in the buffer. Okay, like in a buffer circuit. Okay, of unity gain. And of course, in order to do so, the circuit can be modified as follows. This is Vn. This is the resistor. This is the capacitor. Okay, and we have a unity gain. Okay, this is V out, and here we have a capacitor, another capacitor, because it is a low pass filter. This is C2, this is C1, this is R2, and this is R1. Okay, yes. Once we say unity gain, R3 will be infinity and R4 equal to 0. R3 is equal to infinity and R4 is equal to 0. Now, the transfer function that relate the output to the input of this modified version is given for us by the following transfer function, and we should be able to determine this transfer function. Okay, you just label the node. This is the ground, this is V out. Okay, therefore this is V out. Okay, this is V out, label this VA and solve for 2 nodes, then substitute VA on the second equation, then you end up with only V input and output equation. Okay, then you can relate V in to V out. Okay, transfer function. And remember, once we say transfer function, we take into consideration that the initial conditions are 0. No initial energy stored inside the capacitor. Now we are asked to define A0, A1, and B1. Okay, from this transfer function. Okay, you may be asked on the actual exam, to be able to derive this equation. Okay, you should be able to do so. Alright, so what is A0? Okay, by comparison, we know that of second order, we have A0 over 1 plus A1s plus B1s squared. Okay, by comparison, A0 is equal to 1, A1 is equal to this component, omega C, the cutoff frequency, C1, R1 plus R2, and A2 is equal to omega C squared R B2. This is B1. Okay, sorry. B1 is equal to, let me look over this. Okay. Omega C squared R1, R2, C1, C2. Okay, good. Now we are asked to design and show a schematic of a second order with a unity gain, of course, sallen key, unity gain, sallen key, Chebyshev low pass filter with a corner frequency of 3 kHz and 3 decibels passband ripples, such that C2 is greater than C1 for B1 over A1 squared. Okay, because we need a second order Chebyshev low pass filter, okay, with a 3 decibel passband ripples, we need to refer to the table in order to determine those coefficients A1 and B1 of second order. Okay. Sorry, we need to go back. Okay, so we have a Chebyshev filter, we have a Butterworth filter. Okay, we should pay attention which table we are using. This is the Chebyshev coefficient of 3 decibels, passband ripple. Okay, we need the second order filter. Okay, second order. Okay, we have A1 is equal to 1.065 and B1 1.9305. Okay, so we can return back. So from table we find out that A1 is equal to 1.065 and B1 is equal to 1.9303. Alright, and we are given the cutoff frequency. Okay, the angular frequency is equal to pi fc, therefore this is equal to 2 pi 3 times 10 power 3. Okay, 6 pi 9 pi, this is 2. Okay, 6 pi times 10 power 3. Okay, radian per second. Okay, in order to do so, we need to solve, we need to find the resistance and the capacitors. Okay, we need to find the resistors and the capacitors of the Sankey. Okay, we are given a condition that C2 must be greater than C1. So we can assume C1, choose C1, okay, and find the C2, and then we solve for R1 and R2. If this condition is not given for us, then we can choose C1 and C2 randomly, and we solve for R1 and R2. Usually I take C1 is equal to C2. Okay. In this case, we are given this condition that C2 for practicality. In practice, this is given. If we solve this characteristic equation in order to determine R1 and R2 easily, we need to have C2 greater than C1 for B1 over A1 square. So assume or let C1 is equal to 22 nanofarad, then C2 greater than or equal 22 nanofarad multiplied by 4, B1 1.9303 over 1.065, and this is equal approximately 150 nanofarad. Okay, now we can substitute on those two equations to solve R1 and R2. We have two equations to unknown. Okay, so the first one, A1 is equal to 1.065 is equal to omega C, which is 6 pi times 10 power 3. C1, it is 22, remember, nanofarad, okay, minus 9, R1 plus R2. In the second equation, we have 1.9303 equal to omega C, 6 pi times 10 power 3 squared, R1, which is to be determined, R2, okay, and C1, C2, 22 times 10 power minus 9, and C2 is 150 times 10 power minus 9. Okay, we have two equations, two unknown. You can find, you can bring those numbers to the other side, find R1 equals to some number over R2, substitute it in the first equation. So you have this equation all with R1. You can solve for R1, and you must be able to verify that R1 is equal to 1.26 kilo ohm. And then once you find R1, you substitute in this equation, you solve for R2, okay, which is equal to 1.3 kilo ohm. Okay, so your job is to make a decision which capacitors to use and to find for the resistors and solve for the resistors. Or alternatively, you can assume the resistor values and solve for the capacitors. Okay. Great. Okay. Now we shouldn't forget the second part. We designed it. I mean, we find the values. Now we need to provide the schematic, the final schematic of the Chebyshev low-pass filter of second order. Okay, the Chebyshev of second order is given as follows. This is a resistor, another resistor, and we have a capacitor. Okay, and this is a unity feedback. Okay, here we have a capacitor. Okay, here we have the input, here we have the output, and the capacitance. Okay, this is equal to 22 nanofarad. This is 150 nanofarad. Okay, just to make sure. Yes, this is C2, this is C1. Yes, and R1 1.26 kilo ohm and R2 1.3 kilo ohm. Of course, you may need to round for the resistance in case you don't have something available on the lab. Okay, so you may take, instead of 1.26, maybe 1.3 as well. Okay, so you may play on the resistance with some percentage, and you should take this into consideration in your calculation. Okay, so you say, for instance, for example, R1, the actual R used is equal to R plus 10% or 1% of the R, based on what you have in the laboratory. Okay, now you are asked to design a fifth order with a unity gain Butterworth. Again, unity gain, I mean, we have a unity gain, a feedback 1. Okay, design a fifth order. Fifth order, if we return to the table, in order to design a fifth order, we need a first order cascaded with a second order, cascaded with a second order. Okay, this is the fifth order. Okay, so let me draw it here. Okay, so we have the input. Okay, we need first order. Okay, therefore we need to determine A1, and of course B is equal to 0 in the first order. We have second order. We have A2, B2, and we need another second order filter. We need to determine A3, B3, and we get A output. This, by cascading the first order with two second orders, this would end up with a Butterworth low-pass filter of fifth order. Okay, so because it's a Butterworth filter, we need to refer to the table of Butterworth. Okay, not Chebyshev. This is for Butterworth. We need of fifth order. Okay, this is the first part of the filter. This is the second part. This is the third part. So we need to take those values. So this is A1, and this is B1, which is equal to 0. This is A2. Okay, A2. This is B2 is equal to 1. This is B3, and this is A3. Okay, this is a fifth order Butterworth low-pass filter. Okay, so we have the values from the table. Now we can use them. Okay, so the filter. Okay, let me write down the parameters. So the first filter. Okay, first order filter. Let's say this is the first filter. This is the second filter. This is the third one. So the first filter, okay, has A1 is equal to 1 and B1 equal to 0. Second second filter, okay, has A2 equal 1.6 from the table. Okay, B2 is equal to 1. Third filter has A3 0.618, and B3 is equal to 1. Now remember that we already designed the first and the second filter, second order filters. This is the second order, okay, with unity gain, and this is the second order, and this is the where, okay, and this is the first order, okay. And you have all the parameters and you have all the equations, you have the transfer functions, you know A1 is equal to omega CR1 for the first filter, first order filter. Okay, sorry for that. Okay, so let me give you the drawing. Okay, so the first order, okay, you have first order a resistor and a capacitor, and in order to have a unity gain you need a buffer. Okay, this is a unity feedback. Okay, this is Vn, and this is the capacitance. Okay, and this is the resistance, and you need to determine R1 and C1. You need to determine R1, C1 based on the table of the parameters. You have A1, and you have the relation A1 to R1, C1. We did this already on the first part. Now this first part is cascaded with the second order. The second order design is given by that. Okay, this is the design and this is the transfer function. Okay, we can use it. Okay, this is a resistor cascaded with another resistor. You have a capacitor, ground, you have a capacitor, okay, and you have a unity feedback. Okay, okay, so this is the second part, this is the second filter, and you have those parameters. Now the third filter, okay, the third filter has those coefficients A3 and B3. Okay, as well, it's a second order. Okay, we need to draw this. In case you are asked, for instance, for a third order filter, it is enough to stop here. Okay, third order, you have first order and a second order cascaded together. Okay. You have a resistor, and this is a unity feedback. You have a capacitor here and a capacitor. Okay, and your job is to determine those values of those resistors and those capacitors. For instance, R1, R2, C1, C2. Of course, this is R1 prime. I mean, how could we differentiate those? Okay, make sure not to confuse between this R1 and R1. So let's say this is R1 prime. This is R2 prime, C1 prime, C2 prime. This is double prime. Okay, C1 double prime, C2 double prime, and this is R2 double prime. Our job is to solve for R1, C1 and the rest, and we already did that. Okay, so on the first one, let's take on the first one. Okay, take C1. Let me change the color. Okay, take for instance C1 is equal to 1 nanofarad. Okay, now you need to solve for R1. Okay, and you know that A1 is equal to R1 C1 omega C, right? Okay, and you have the cutoff frequency for each filter is 50 Hertz. Okay, the cutoff frequency is given as 50 kilohertz. Okay, 50 times 10 power 3 Hertz. Now to solve for R1, this is equal to R1 equal to A1 over C1 omega C, and A1 is equal to 1. Okay, 1 over R1 C1 omega C, which is equal to pi Fc. Okay, this is A1. Now we substitute. Okay, this is 1 over 1 nanofarad times 10 power minus 9 2 pi FC 50 times 10 power 3. Okay, and this is equal to 3.18 kilo ohms. Now, so we determined for the first part of the filter the capacitance and the resistance, okay, the values of the resistance and the capacitor. Now we need to solve for R1 prime, R2 prime, C1 prime, C2 prime, okay. And remember, guys, again, you need, maybe you will not be able to find like 3.18. The closest value you can find it is 3.16 on a practice, okay. So you may choose not exactly 3.18, you may choose 3.16, and you consider the unprecision value of 1%, okay, approximately, okay. So the closest 1% value is 3.16, okay. Let me write it down. The closest 1% value is actually 3.16 kilo ohm in practice. Okay, now to solve for C1 R1, now again you should be looking over the transfer function of this second part. This is the transfer function, this is A1 and this is A2. Okay, as we did on this part, we assumed C1, we solved for C2, as if we assumed C1 and C2, and we solved for R1. And that's what we are going to do in this case. So let us take C1 is equal to 820 picofarad, okay. In order to solve for C2, okay, picofarad is 10 power minus 12, must be greater than equal. Let me C1 for B1, okay, how those prime for B1, we label them for the second filter P2, so I will be using P2, okay, A2, okay, square. This is equal to 820. A1 is, P2 is 1 over A2 is 1.618 square. Okay, and this is equal to 1.26 nanofarad. So now we determined C1 and C2, we assumed, and now we need to solve for R1 and R2 based on the transfer function, on the characteristic equation of this filter. Okay, we have this equation and we have this equation. A1 is equal to okay, let me write it. A1 is equal to 0.618 directly, equal to omega c C1 R1 plus R2. Omega c 2 pi f 250 times 10 power 3. Okay, the cutoff frequency is 50. Okay, multiplied. So I'm using this one. Okay, A1 is equal to omega c based on the characteristic equation. Okay, this is A1 or A2 mainly. Okay, omega c C1 R1 R2. C1 820 times 10 power minus 9. Okay, need some space. R1 plus R2. And the second one is B2 is equal to omega c square R1 R2 C1 C2. Okay, and B2 is equal to 1. So B2 is equal to 1 omega c squared R1 R2 C1 C2 1.26 times 10 power minus 12. You have two equations to unknown. You can solve and verify. R1 is equal to R1 prime just not to confuse those with the first filter. 1.87 okay, kilo ohm, and R2 prime is equal to 4.42 kilo ohm. Alright. Right. Now let's solve for the last filter. It's on the same way we did on the second filter, we will be doing on the third filter. We will assume for C2 prime or C1 prime, double prime, solve for C2, for instance, take C1 double prime equal to 330 picofarad. You should be able to verify C2 double prime is equal to, using this equation. Okay, let me substitute this time. Okay, for B3 is equal to 1 over A3 squared. Okay, 0.618 squared. And this would be equal in order of 3.46 nanofarad. Okay, and it's your job to verify that R1 based on those two equations. You can use A3. Okay, A3 is equal to omega C. Omega C. This is C1. Okay, double prime. Okay, R1 double prime plus R2 double prime. Okay, you substitute A3 with 0.6118 and B3 with 1 equal to omega C squared, R1 double prime, R2 double prime, C1 double prime, C2 double prime, and you solve for R1 double prime equal to 1.45. You should be able to verify this, and R2 double prime is equal to 4.51 kilo ohm. Clear? So this is the beauty of sallen key topology and the tables that make our life easier instead of going and every time solve and assume values and so on in order to obtain a certain type of filter. So it is really easy. We just now in the laboratory we build the same circuit and we put R1 with this value of 3.18 and the capacitance of 1 nanofarad, and then we connect it with this R1 prime is equal to 1.8987 and so on. Okay, so we have the values there. This is called the fifth order filter, and this is a type of Butterworth low pass filter which gives you a flat, okay, a flat response and which is less steep compared to the Chebyshev filter. Okay, and the ripples almost negligible. Okay, in the Butterworth filter. Okay, because Q is equal to 1 over radical 2. Sallen key is really powerful, is very useful, and we have a question number 3 as well, is based on the sallen key topology. Okay, on the sallen key topology. Okay, and if we look over the table, okay, this is the sallen key. Okay, this is a low pass because we have here the capacitors. If it is a high pass, then we have, instead of R1, we switch R1 and R2 with C1 and C2. Okay, we switch them. Okay, we have the transfer function, we have the cutoff frequency, we have the selectivity or the peakness of the filter, we have K. Okay, and we have special conditions. Okay, we have special case 1, special case 2, special case 3. Now, if we are given this filter, okay, this filter, and this filter, as you can see, of unity gain, the actual filter is like that. So R3 is infinity and R4 is equal to 0 to have a unity gain, right? A unity gain. Therefore, if you have a unity gain, okay, unity gain, K must be equal to 1. And the second condition is that R1 and R2 are equal. So you need to know which case to use, right? Okay, so we have K equal to 1, and we are given that R1 and R2 are equal. So we use directly the special case 1. Okay, and K1 is equal to 1. Okay. Okay, and you have the quality factor Q is equal to 3. So then it would be really easy, right? So C1, let's then use, okay, make use of special case 1. Okay, the special case 1, you have C1 is equal to Q over omega 0, the corner frequency or cutoff frequency, 1 over R1 plus 1 over R2. All of those are given to you. Omega 0 is given as well, which is 2 pi f0. Okay, radians per second. So this would be the quality. I mean, because R1 and R2 are equal, we can write it as Q over 2 pi f0, 1 over R1 plus this is equal to 2 over R in general, such that R is equal to R1 equal R2 equal to what is given to us, 2.2 kilo ohm. So the peakness or the quality of the filter or the selectivity of the filter is given by 3 times 2 over 2 pi, okay, you can cancel 2 with 2, pi f0, okay? And you have R is equal to 0.2 times 10 power 3 ohms. This is equal to 434 nanofarad. Now in order to determine C2, okay, this is C1, this is C1, C2 is equal 1 over Q omega 0 R1 plus R2. Okay, then C2 is equal to 1 over Q omega 0 R1 plus R2. And this is equal to 1 over, this is 2R multiplied by 2 pi, which is 4 pi f0, multiplied by 2.2 times 10 power 3, which is equal to 12 nanofarad. As simple as that. So we just select the resistors R1 and R2 2.2, and the capacitors must be C1. Okay, this is 2.2 kilo ohm. This is 2.2 kilo ohm. C1 is 434 nanofarad, and C2 is equal to 12 nanofarad. Then this filter is of second order and has a corner frequency of 100 or 1000 hertz, and this is a low pass filter. Okay. The last question we have, find the quality factor of the following bandpass filter. This is called bandpass filter with the following frequency plot, and the frequency plot is given by the body plot. Okay, and your job is to find the quality factor. In order to find the quality factor, we notice that the quality or the selectivity or the peakness is given by the f0, the corner frequency, over the bandwidth. Okay, and the bandwidth is given by the upper frequency minus the lower frequency. So your job is to find f0, f upper, and f lower from the graph. Remember, this is a logarithmic graph. So here we have 10, then we have 10, 20. I mean, the x-axis we have 1, 2, 3, 4, 5, 6, 7, 8 till 9. Then we jump 10 by 10. Then we jump 100 by 100. Okay, so here we have 10, 20, 30, 40, 50, 60, 70 until we reach 100. Then we have 200, 300, 400, this is 400, okay, which is on the middle, okay. Okay, this is F0, okay. Okay, so this is F0, it is approximately 400 Hertz. Now once we reach 400, 500, 600, 1000, then we have 2000, 3000, 4000 and so on. Alright, in order to determine F upper and F lower, we need, we used to have like 1 over radical 2 of the output, 0.707 from the output. But now the curve is given in logarithmic decibels. Okay, what the meaning? The frequencies must be lower than the peak. Okay, by 0. Okay, usually we have then those frequencies are lower than the peak value. This value, the peak one, they are lower by 0.071 over radical 2. Okay, but in decibels we can convert it into minus 20 log 1 over radical 2. Okay, in order to obtain the unit of decibels. Okay, minus 20 log 1 over radical 2, which is approximately 3 decibels. So we needed to have a value which is less than 3 decibels of those values. Okay, so here we have, okay, approximately 23. We need to take this line less than 3 decibels. Okay, we get this line, and our job is to determine the intersection. This is the F lower and this is the F upper. So this is approximately, so if this is 20, this is 30, this is approximately 27 Hertz. This is F lower, and this is 1000. Here we have 2000, 3000, 4000. 6000 Hertz. Okay, this is the quality. The much more it is, we have a peak, the much more we are selective. Okay, so the range between the upper and the lower must be lower. Okay, the smaller we have, okay, this bandwidth range, the more we are selective, and the peakness increases. Okay, the peakness increases. So therefore Q is equal to 400 over 6000 minus 27, and you should be able to determine the quality or the peakness or the selectivity of this bandpass filter. Thank you, and hope you will be doing very well on the exam that is going to be on Thursday. See you.